Hi folks, this is the Unit 6 Day 2 lesson. We're going to look at finding maximum or minimum on a specific interval of a function. So looking at this graph here, the first question says, what's the maximum of the function on the interval -5 to -2? So I'm just going to highlight that piece of the function. So from -5 to -2, if I kind of highlight along that function there, what's the maximum value? So the maximum would be here at that point. So the max is y equals 5. So that's the maximum value that happens in that interval. Now, the next one says, what's the minimum value of the function in the interval 0 to 3? So I'm going to kind of go back in a different color and highlight the function, highlight the graph of the function between 0 and 3. And here we're looking for a minimum value. So that would be there, the lowest value in that green highlighted section would be a minimum of y equals -2. And that's usually where we expect to find maximums and minimums. So here we've got turning points, and that's often what we think of as the maximum or minimum. It's not always the maximum or minimum though. If we were looking at part C, and I'm just going to erase my other highlighting here from the previous one, here we can look at this and say we want to find the minimum of the function on the interval from -4.5 to 0. So again, I'm just going to erase other highlighting. Now, this minimum doesn't actually happen at a turning point. So the minimum from -4.5 to 0, I've highlighted that. There is a turning point here. There's a turning point at that part there. And that is like a minimum value. That's what's called a local minimum. But the actual lowest point, if you wanted to know where the minimum cost was or the minimum volume or whatever you might be looking for, the actual lowest point is over here at about -3. So that would be the actual lowest point there for that one. So the minimum isn't necessarily just the turning points. It could be the end points of the interval that you're looking at. So an absolute extreme value is the actual highest or lowest value in an interval. Turning points are called local minimums or local maximums. So neither of these 2 points that I've labeled as a local minimum is the lowest value on the function. The lowest value on the function would happen as it continues off in big negative numbers. You can have a local maximum at a turning point, and that may or may not be the absolute maximum of the interval. It depends what interval you're looking at. So we know that the maximums and minimums can happen as at turning points, and that would be where the derivative equals 0. But they can also happen at the endpoints of the interval. I'm also going to add that we're going to check points where the derivative does not exist. And the common example we see of this is something where there's a cusp and you can't find the derivative at pointy parts of your graph. So we're also going to check where derivatives might not exist. And if you substitute these values in and say, okay, where is the highest one and where is the lowest one? So we're going to go through kind of a process. We're going to find the derivative, find where that derivative equals 0, and where it doesn't exist if that's part of the function. And then we're going to test the endpoints and those critical numbers of the derivative. So for this one, we've got f at x equals negative 2x cubed plus 9x squared plus 4. So we want to find our derivative. So that's negative 6x squared plus 18x, and find where the derivative equals 0. This is why we were factoring so much in our previous derivative work. So the critical numbers, I just shorten that CN, is where f prime at x equals 0 or f prime at x does not exist. Now, where does the derivative equal 0? That would happen at x equals 0 and x equals 3. Where does it not exist? There's no points where this derivative's not defined. So then we're going to check, and note that you're going back into checking the original function. So I'm going to check f at 0, f at 3, but also the endpoints, f at negative 1 and f at 5. So I would go back and substitute these into the original function, and f at 0 is going to be 4. F at 3 is 31. F at negative 1 is 15. And f at 5 is negative 21. So we can find the minimum and maximum just by looking for the highest and the lowest points. So you just look for the biggest and the smallest y values. So there's a maximum of 31 at x equals 3 and a minimum of negative 21 at x equals 5. So here, kind of a similar situation. We've got this function for our height and time. I think that we can reasonably say that time is greater than or equal to 0. So if we got a negative value, we wouldn't worry about it. So we'll find where does that derivative equal 0. So the derivative of this function is negative 10t plus 30. So negative 10 times t minus 3. So the critical numbers, s prime at t equals 0 would be a time of 3, and s prime at t does not exist. We're not going to include any of those. There's no restrictions. So then we're going to check s at 0 and s at 3. So the height at 0 is 1, and at time equals 3, we would have 46 meters. And we know that after it's 3, for bigger numbers than 3, this whole thing is going to be negative. So we know that this graph is a parabola opening downwards. So we know that that height would be the maximum, even though we don't have an end point to our interval. So it's a max height of 46 meters at t equals 3. Okay. Now here we're looking at what is the velocity of the ball when it's caught 1 meter above the ground. So we know that the velocity function is the derivative of that height function. So that was our negative 10t plus 30. And we want to figure out if my height, s at t equals 1, we need to find the time when that happens. So I'm going to substitute 1 in and solve for t. So the two 1s will cancel out, which is kind of nice. So 0 equals negative 5t times t minus 6. T equals 0 or t equals 6. So at time equals 0, that's not when the ball's caught, that's when it's thrown. And time equals 6 is when it's caught. So we want to find v at 6. So that would be negative 10 times 6 plus 30, which equals to negative 30, and that's in meters per second. So therefore the velocity is negative 30 meters per second when the ball is caught. Now, is the ball speeding up or slowing down when it's caught? So we know already from the last one that that's at t equals 6. So remember from the first day, speeding up means v and a signs match. So if something's speeding up, the velocity and acceleration have the same sign. If it's slowing down, the velocity and the acceleration have opposite signs. So here we've got our velocity function was negative 10t plus 30, and the acceleration, which would be the derivative of the velocity, is just negative 10. So we knew that v at 6 was negative 30 meters per second, and a at 6 is negative 10 meters per second squared. That's just constant, doesn't matter what your x is. Okay, so because v at 6 is negative and a at 6 is also negative, the ball is speeding up. If those signs match, it means that it's going faster and faster in either the positive or the negative direction. Okay, we want to figure out on a scale of 0 to 10 how effective your studying is. So this says the student has 30 hours to study. So I'm going to restrict our time. They could study not at all or up to 30 hours. We want to know what's the maximum effectiveness for their studying. And I just have this on another slide. So I know that t is between 0 and 30. So here I'm going to simplify this first. I'm going to multiply this 0.5 in. So I get 5 plus 0.5 t times e to the exponent negative t over 20. Then the derivative of that, the derivative of 5 is just gone. And now I have to look at this as a product rule. So I'm going to put the 0.5t as one factor and then the e to the negative t over 20 as the other. So here I have the first factor, so 0.5t times the derivative of the second, so that's e to the negative t over 20 times the derivative of the exponent, which is negative 1 over 20, plus we'll do the second factor, so e to the negative t over 20 times the derivative of the first, which is 0.5. I may actually just write that as 1/2. So here we've got, I'm actually going to change all my 0.5s to 1/2 just because I've got some fractions and some decimals. So I'm just going to clean this up a little bit. So I have negative 1 over 40 t e to the negative t over 20 plus 1/2 e to the negative t over 20. So now I want to make sure I factor here. So I'm going to factor out negative 1 over 40 e to the negative t over 20. And here I get t minus 20. Because 20 times 1/40 is 1/2. Now I want to know when e prime at t equals 0 for my critical numbers, or when the derivative does not exist. And there aren't any restrictions on my derivative. This is a continuous function for all values of t. It would equal 0 though when t equals 20. Note that that comes just from inside the bracket. This is an exponential function, so you don't actually have any restrictions, or you don't have any times when that e to some exponent could be 0, because you can't put any exponent on a positive number and make that answer equal to 0. So I would check, go back into your original function and check e at 0, e at 20, and e at 30. And then that's what we want to find the best value here. So if you take a 0, sub that into your original function, take a 20, sub it into your original function. So my best value is 20, because I get about 8.68. If I sub in a 0, I get just 5, and if I sub in 30, I get about 8.34. So the maximum effectiveness is 8.68 at 20 hours of studying. Maybe if you studied too much longer, you'd be too tired for your exam. Anyway, that is the Unit 6, Day 2.